recording. Right, so it's a great pleasure to have Nani Seiberg from the IAS, and he'll talk about proliferation transitions from a 2+1d TQFT. Please take it away.
Thank you. Thank you for inviting me, and good morning or good evening or whatever your time zone is. As you can see on this screen, I thank the ultra quantum matter collaboration, even though it's almost essentially over. And the reason this is I thank for them specifically here is that this would be a rather interdisciplinary talk. There would be connections to condensed matter physics, connections to math, and primarily I'll talk from the quantum field theory perspective, which is my own background. And in this context, I also want to thank Senthil for endless hours of discussions, fighting, arguing, etc., in the typical Nati/Senthil style. And I'll talk about work with Monk Cheng, which hopefully will be out within a few days. So the 2026, I think, is quite realistic, unless we really hit a major disaster. And even though it's a Zoom call, please feel free to interrupt me and ask questions. Just yell and I will be here. So let me start with some general comment about TQFTs. We'll be interested in TQFTs, and given a TQFT, we can have maps between TQFTs. This is not a field theory map, but it's a map between different field theories. In this case, these are TQFTs. So one thing we can do is consider tensor products. This is called stacking. We take product of two theories. We can also gauge an anomaly-free one-form symmetry. I'll say more about that later. And this is misleadingly referred to as anion condensation. I will also explain later why I think very strongly that this is very bad terminology. We can also gauge a zero-form global symmetry. That depends on more data. In field theory, we call it adding counter terms. In condensed matter physics, it's calling tensoring an SPT. And the example here would be, an example would be Dykert-Witten terms. And then we can do it again. We can stack something and again gauge and so forth. And we can have a tour in the space of TQFTs, finding new ones. And a special case of that, which will be important later in the talk, is the hierarchy construction in quantum Hall. And again, for some reason, this is also called anion condensation. So I can give a whole lecture just about why everything should or should not be called anion condensation, but I put the term here mostly to relate to people who are familiar with it. So let's start with a little history lesson about gauging a one-form symmetry. This story goes back to 89, and this is work that I did with Greg Moore. And at the time, it wasn't called gauging a one-form symmetry, but it was called extending the chiral algebra in an RCFT, or considering a quotient of the gauge group in the Chern-Simons theory. So let's do what happens when we gauge an ordinary zero-form symmetry. If the symmetry is discrete, we have to sum over bundles. And the sum over bundles is obtained by dividing space-time into patches with transition functions between them. And every time we have a transition function, along the transition function, we have a symmetry defect. So gauging a zero-form symmetry is the same as summing over all possible symmetry defects. This is familiar in 1+1 dimensions in the context of orbifolds, and we can do the same thing in higher dimensions. And we can say that the symmetry defects, which in 2+1 dimensions are surfaces, proliferate. So we sum over them. If we consider a one-form symmetry, then the symmetry operators are lines, and my color coding in this talk will always be this blue. So these blue are the symmetry lines, and they proliferate. So this is a physical line that exists there, and we're not going to sum over it. And the process of gauging amounts to summing over all possible insertions of the blue lines. So pragmatically, we start with a bosonic TQFT. For simplicity, in this talk, I will talk only about bosonic theories. And I single out an abelian anion, A. The anion has order n. N is determined by the power of the anion, that is 1. And that leads us to another TQFT, which I'll denote as T prime. And I'll write it either as a quotient T, the original theory, modded out by Zn, or specifically which anion generates this Zn. This is this notation. And this notation, thinking of gauging as quotient, also is satisfying conceptually, but also from the point of view of Chern-Simons theory, this is an actual quotient of the gauge group. We can consider SU3 and T being an SU3 Chern-Simons theory or SU3 mod Z3. And this can be done in a consistent way only when A is a boson. And a boson means that the dimension of the operator O in the RCFT, or the spin of the anion A, is an integer. I emphasize, and that will be important later, that in the context of TQFT, only H modulo 1 is meaningful. So once we have this condition of anomaly freedom, there is no braiding of A, and therefore the sum over A is consistent. So the summary of this slide is that gauging is proliferation of anion lines. Let's move on. Once we have a one-form symmetry and we gauge it, we get a new dual symmetry. In the context of orbifolds, it's known as a quantum symmetry. Think in condensed matter physics, the terminology is dual. So when we gauge a one-form symmetry, Zn with superscript 1, we get a zero-form symmetry, a Zn zero-form symmetry. And typically, this symmetry is not faithful. What I mean by that is that it does not act on the resulting TQFT. It's not a symmetry of the TQFT. There are no surface operator or symmetry defects for this zero-form symmetry. But the subgroup of it can act faithfully, and it acts on the twisted sector lines. So in terms of my colors, red is the typical line in the TQFT, and the blue is the line that I sum over. If I sum over the blue line, then I can have lines that end on the red line, and then within the sum over the blue lines, I have to sum over different configurations, and some linear combinations of these could lead to new states that are being permuted by a subgroup of the zero-form symmetry. All that is well known and was fully understood by the previous millennium. Now I want to emphasize that gauging should not be viewed as condensation. The history of that was that the word condensation actually appeared already in the original paper I wrote with Greg and in a follow-up paper that Greg wrote with Nick Reed. But it really became popular by the work of Bice and Singleland almost 20 years later, 2009. And I remember at the time I was very upset because I did not see the condensation here. And the reason is, first of all, gauging is a map between TQFTs rather than a phase transition. I emphasized it earlier in the talk. I started with maps between TQFTs. I started with a map between TQFTs. And gauging is a map between TQFTs. But condensation means that there's a phase transition, and there's no phase transition here. Second, even if we implement it by a phase transition, which we will do below, the condensation means that the global symmetry is spontaneously broken. Condensation means that a certain operator gets an expectation value. And for an operator, a local operator, a point operator, to get an expectation value, and for this to be meaningful, this operator should carry a symmetry, because otherwise it can mix with the identity. So it can carry a symmetry, it can transform under some symmetry, and when this is the case, the symmetry is spontaneously broken. The process of gauging a one-form symmetry does not involve any symmetry breaking. In fact, it involves explicit symmetry breaking, because some of the symmetry lines of the original theory are no longer symmetry lines after gauging. So that symmetry is explicitly broken. This can be described as due to an anomaly. So the situation here is similar to the BKT transition. Before the transition, the winding symmetry or the vortex symmetry was an emergent symmetry. After the symmetry, that symmetry is explicitly broken because the corresponding vertex operator is relevant. And indeed, the BKT transition, people who are careful about terminology refer to it as proliferation of vortices rather than condensation of vortices. Even though I said that, many people still don't see the distinction between them. Now, even if we accept that we are careless about the terminology, I should say that what really proliferates here is not the anyons, but the anion lines. It's not that we have a lot of anyons in the background, but instead we have a lot of anion lines. So this was my rant against the C word. Now let's see whether we can find a phase transition that implements gauging. So we are going to look for a non-topological field theory with two phases. One phase is the original TQFT, and the other is the gauge version. So here is the phase diagram. We have a parameter mu square, for example, the mass square of a scalar field, and we tune it from being, my convention is that here it is positive and here it is negative. So here, in this phase, we have the original TQFT, and in this phase, around here, we find the new TQFT, which is the quotient. And what we're looking for is a field theory, non-topological field theory, that describes this phase transition between the two phases. So how should we go about doing that? Naively, it should be the Chern-Simons theory for T. We start from T. This is our starting point. And we have a special anion A. And we would like this anion to do something so that we can find the other phase. So naively, we should look for a Chern-Simons theory for T and have a scalar field for A. And then this scalar field will develop an expectation value and Higgs the gauge group for on the left side and trigger the transition. So here, again, we have this dichotomy in terminology. There are two things here which we should really distinguish between. Both of them are referred to as condensation, and none of them should actually be called condensation. One is the gauging, which is a map from this phase to that phase, and the proliferation transition is a non-topological theory that describes this transition between the two phases. Now, I remember very clearly in 2007, Mason and Mong visited IAS, and a bunch of my students and postdocs were there. We spent great time together, and I complained about exactly these issues. And the following day, Mason showed me that they can actually find such a phase transition, and I was completely stunned by it. So you can actually find a phase transition that does this gauging. And I later learned more about that from Poshen and Hotat. So they found an algorithm that I will soon review that starting from TQFT and the anion A that you would like to proliferate, they exhibited a UV field theory that implements this transition. Given that, we can ask more generally, can we find more transitions? Can we proliferate anions that correspond to an anomalous symmetry? Anomalous one-fold symmetry. Can we generalize it more? And physically, what we have in mind is a TQFT. We have a topological order, some phase, and as we approach the transition point, an anion becomes light, maybe a number of anions become light, and we would like to make these anions dynamical, couple them to the TQFT in such a way that we can find the other phase. So we are going in general we're going to study a general, possibly non-abelian TQFT, not necessarily abelian, and I'm going to choose in a one-form symmetry carried by this generated by this abelian anion A. It would be a ZN symmetry, and the N here is the order of the anion, determines here which power is 1. And that symmetry has an anomaly determined by the spin of the anion A, which is P over 2n. So the anomaly depends only on P mod 2n, but as you will soon see, we're going to view P as an arbitrary integer. And again, I emphasize we study only bosonic theories for simplicity. So our goal is to find a field theory for T coupled to a dynamical A, and we look for a Chern-Simons Lagrangian based on that gauge group G for T and phi. So let me unpack this long sentence. We start with T, and we have an anion A, and we would like to make A dynamical. It's very hard to write a field theory for anyons because the anyons do not correspond to ordinary fields. The anyons in the field theory will not be gauge invariant. So therefore, we'll have to be a little bit careful. So our strategy is kind of straightforward. We start from a theory T, TQFT, and we find the Chern-Simons description of it based on some gauge group G for T. And now we throw in a scalar field phi in an appropriate representations of G such that we can find the transition. So this framework has been studied by many, many people from many different perspectives. I would guess that there are several thousand papers discussing Chern-Simons matter theories, different gauge groups, different representations, there are interesting dualities, it appears with various supersymmetries, etc. The first problem we face is that given the TQFT, the anion A, this field theory is not unique. And there are several ambiguities here. First, when we start with T, with the TQFT, there's an infinite number of gauge groups G and appropriate levels that represent the same T. So that's the first issue. Which gauge group are we going to pick? There's an infinite number of options. Even if we pick one of them, it's typically the case that there's an infinite number of representations of G that all correspond to the same anion A. For example, U1 level K has K different anions, but U1 has an infinite number of representations labeled by an integer. So which of them should we pick? And to make it more extreme, in some cases, the anion A does not correspond to a particular representation of the gauge group, but it is associated, it is a magnetic one. It is characterized by the holonomy around the line. I pause for questions here. Can you hear me?
Yes.
We can hear you.
You can hear me, but there are no questions. Okay, thank you. So I guess I'll speed up. So let's start with the abelian theory and have a concrete example.
Please don't
so that we
speed
know
up, Nadi.
Who said that? Greg, was that too
Greg said
slow
that.
for
Please
you?
don't speed up.
Okay. So we're going to start with an abelian theory, primarily in order to have a very concrete situation where we can analyze it. And again, there is huge literature. And I gave one reference here to the paper of Wen and Wu from 93, but there were many papers before that and many papers after that denoted by these ellipses. So this is the Lagrangian, and I'll be a little bit careless. Hope Greg will not object. This is a form, and this is a scalar, but this is standard in this business. We just add them together and we know what we mean. Otherwise, I'll have to write too much. So what do we see here? If we ignore these terms with phi, which is the case if phi is very heavy, so imagine mu square is positive and large, we can forget about phi, and we have just a TQFT described by this abelian theory. I think that's analyzed in a lot of detail by Belov and Moore. And what does phi do? Phi is still a heavy field in this phase, and phi is not gauge invariant, so it is attached to a Wilson line. It is attached to this Wilson line. Therefore, phi corresponds to a particular anion in this abelian TQFT. So what we've achieved here is to write a field theory. It's a massive field theory. It's non-topological. At low energies, it looks like a TQFT. But unlike a TQFT, where the anion A is a defect, here the anion A is a dynamical particle, and it is described by phi attached to this line. So now let's put some more meat on it. The order of the anion is determined by solving this equation. So we ask, what's the smallest positive integer n, so that all these numbers are integers, and that would tell us what power of A is the trivial anion of the TQFT. We'll also find it convenient to define this integer n, this integer p, which we take this thing and we dot it to a vector of integers, this qi. And one significance of this p is that p mod 2n determines the spin of the anion A. So the spin of the anion A is p over 2n mod 1, and therefore at the level of the TQFT, only p mod 2n is relevant. So ignoring again all the terms with phi, we have an abelian theory with k matrix K and the anion A labeled by a q vector q. So we have an infinite number of k's and an infinite number of q's corresponding to the same TQFTs. So at the level of a TQFT person would say, we describe the system in a very inefficient way because we have infinite number of k's and infinite number of q's that lead to the same TQFT. But however, they lead to different field theories here, because some of the manipulations that tell us that several k's are the same or several q's are the same are not valid when we add the scalar field. So we should really reanalyze which theories are the same and which theories are not the same. In particular, that would be important for us if we keep k the same and we change p by adding 2n to it. That does not affect the TQFT data, but it does affect the field theory. So as we will see, we'll have different field theories labeled by an integer p, even when p mod 2n is the same. So let's discuss it in a little bit more detail. This is the field theory. If mu square is positive, we have a gapped phase, and we can forget about these terms. And we have at low energies only the TQFT. If, however, mu square is negative, we have a gapped phase. What happens is that phi gets an expectation value that's a little bit imprecise, but phi Higgses the gauge group. And we have a new field theory corresponding to some T prime, and I'll discuss it in more detail below. Now, for p not equal to 0, if the integer p turns out not to be 0, this construction happens to be the same as the abelian hierarchy construction of Haldane and Halprin. What they said was that we have a TQFT and an anion A, and imagine we change the parameter such that we have lots of the anions A, and these anions form their own fractional quantum Hall state. So personally, I always thought this was beautiful, but I didn't understand what this thing means in terms of field theory. How do I describe in field theory the process of adding more and more anions and then changing the system such that these anions form their own fractional quantum Hall state? And now I'm very happy that I do know what it means. It's described by this Lagrangian. So this intuitive picture of Haldane and Halprin is a Higgs transition in this Lagrangian. So for non-zero p, and I haven't shown it yet, but I will show a little bit of that later, this Lagrangian exhibits a transition when mu square is positive or mu square is negative, which performs exactly this abelian hierarchy construction of Haldane and Halprin. And for p equals 0, this Lagrangian is similar to gauging a one-form symmetry. What I'm saying here is not completely precise. I will soon make it more precise. So this is a summary of what can be done with abelian theories. Now let's go to more generic theories, but ourselves to the case p equals 0. So this is the example. The first example of that I saw was U1 level 2 U1 level 8 going to U1 level 2. That was presented to me by Mason and Monk. And then my two former students, Poshen and Hotad, presented to me the general case. And for all I know, these ellipses represent many other people who had the same idea. So we start with T, with an anomaly-free one-form symmetry generated by A. And then we gauge it, because we've already learned how to gauge it, to form T prime. We find this theory. And then once we gauge it, we have a dual zero-form symmetry. I mentioned it earlier. And if we gauge the dual zero-form symmetry, we come back to the original theory T. So that looks like a pointless exercise. We gauge something and then we gauge it back. However, the advantage of doing it is that once we've done that, we've singled out the Zn gauge field in T. So we now have a new presentation of the theory, original theory T, with an explicit Zn gauge field. Once we have an explicit Zn gauge field, we can couple it to phi, and also add the potential phi to the end, which is gauge invariant. And once we do that, the system has two phases. Mu square positive, where phi is massive, and then the IR theory is the original TQFT, or mu square negative, and then phi Higgses that Zn that we see here. And we end up with precisely the quotient theory, or precisely the gauge theory. So the upshot of all that is that this transition theory that was described here in words, we gauge the one-form symmetry, and then we gauge the dual zero-form symmetry, and then we added a scalar field. This transition field theory implements the transition from T to T prime. So this transition field theory is a non-topological theory. On one phase, we have the original TQFT, and in the other phase, we get the gauge version of it. So what have we done so far? We discussed examples of transition field theories.
Naughty. So
Yeah.
you're gauging the zero-form Zn symmetry in T prime, is that right?
Also, step 1, I started with T. Step 2, I gauged the one-form symmetry, which is an anomaly to find T prime.
Yeah. Right.
Then I discover, I shouldn't say I discovered, these people discovered that there is a zero-form symmetry, a dual zero-form symmetry
Right.
that acts on T prime.
Right.
Now we gauge it. Since we gauge it, we go back to the original theory T.
Okay.
Now we have a presentation of T with explicit Zn gauge fields.
So now you do the same story, but coupled to phi, and you
Right.
get something.
So now instead of doing gauging and gauging back, I'm coupling to phi and let phi change the mass square of phi. I'll soon do that in several different ways. I'll reproduce the same procedure. And I really hope that people interrupt me with questions because otherwise I have no idea how I'm doing.
So I have a quick question.
Thank
When you
you.
say when you say p equal to 0, you mean p equal to 0 mod n, mod 2n?
No, I say p equal to 0. When I
Okay.
say p equal to 0, I specifically mean p equal to 0 rather than p equal to 0 mod 2n. This will soon be absolutely crucial.
But this operation that you are describing here is something that you could do also even if p is equal to 0 mod 2n.
Right. That's right. So in the operations on this slide are operations that are mostly at the TQFT level, and they can indeed be done whenever p equals 0 mod 2n. In fact, p as an integer rather than p mod 2n is not even well defined within the TQFT. But in the field theories that I will soon write down, this slide is correct only when p is strictly 0. I need to lift, in the field theory, I will need to lift p to an integer. And once I lift p to an integer, this procedure, as it appears here, is meaningful only when p is actually 0. So you're completely right that at this stage, I could have said p equals 0 mod 2n. But to match with the later part of the talk, I call it p equals 0. Did I answer your question?
Yeah, absolutely. And sorry,
Thank you.
one other quick question. When you gauge back the zero-form symmetry, in general, to reconstruct the original TQFT, you might need to add an SPT phase, right?
That's correct. So the statement here is again a little bit careless. I have to add the appropriate SPT such that I find back T.
Yeah.
So there is such a choice. And this is a really very convoluted way of saying that we have T, because we started with T and we found a new presentation of T that singles out the ZN gauge field.
And that ZN gauge field is sort of like a digraph-Witten field?
I don't know what you mean by Digraph-Witten field. It's a ZN gauge field.
Is it a discrete gauge field?
It is a discrete gauge field.
Okay.
Discrete gauge fields existed decades before the Digraph-Witten paper.
May I ask a question? So, Nari?
Yeah, I see you and hear you.
So, what is the role of adding this term phi to the n in the Lagrangian?
That term will soon be crucial, because if we don't add the phi to the n, the system has a global U1 symmetry rather than the Zn. This will soon be absolutely important.
Okay, thank you.
So far, I'm telling you what I learned from these people more than a long time ago. I learned that almost a decade ago. We're still in the history lesson. So what have we done so far? I posed the question. We have two phases, and we want to see a phase transition between them. It's a proliferation transition. And we discussed two examples. None of them we've done it with a lot of detail. One is T was an abelian theory, and A generated any Zn one-form symmetry with any P. And the other T was any T. It could be abelian or non-abelian, but we focused on an anomaly-free Zn one-form symmetry. That, of course, leads to a bunch of questions. First of all, what is the more general case? We have an arbitrary T and A with any value of P. What should we do then? And if we do that, what is the most general theory that we can find for a given T and A? Not only first was, can we do it at all? And second was, given that we can do it, are there multiple ways of doing it? Once we write a Lagrangian, maybe I'm obsessed with that. I think that when I see a Lagrangian, the first thing I have to understand is what's the global symmetry. What acts faithfully, what does not act faithfully, and so forth. And in particular, how is this related to the symmetries that we see at long distances in the two phases? Once we understand that, we can understand the phases better and see what the different phase transitions are. And of course, once we understand that completely, we can try and generalize that to non-invertible symmetries. And I will tell you right away that I have not done that yet, so we are not going to discuss that. So for the rest of the talk, I will address these questions only for invertible symmetries, and I will soon make another simplifying assumption. So again, we start with the hero of the stories are a TQFT T an abelian anion A, physically it becomes light and becomes dynamical, and then we try to write a field theory for it that triggers the transition to another phase. So again, for simplicity, I'm going to limit myself to bosonic theories, and in bosonic theories, P times N is an even integer. So we look for a Chern-Simons theory for them, and what's the data? I've said earlier that we look for such a Chern-Simons matter theory, but what's the data that we have? We have an integer n, which is the order of the anion, and we have the spin of the anion, which is p mod 2n. And now I'm going to make another simplifying assumption that the scalar field phi is a single complex scalar field, or it is a one-dimensional representation of the gauge group G. If the gauge group is Z2, we could live with the real scalar, but let's leave that aside. And the main point is that given this data, namely the value, the TQFT T, and the choice of anion A, that determines N, and this P mod 2N, and as Andrea asked earlier, so far we have only P mod 2N. Specifying P as an integer gives us a unique construction. There's a canonical field theory that we can use. And for any non-abelian T, and for any anion A that generates a one-form symmetry, including in particular the anomalous ones. So the only remaining freedom is in an integer P with a given P mod 2N. So it's surprising that you can actually do it. And once you've done it, it looks like, oh, there should be many ways of doing it. And the next surprise is that the remaining freedom is only in one integer P. And finally, the surprise is that all the theories that we find, all the transitions that we find are transitions that we know and love. So let me first describe it as a map between two TQFTs. And for simplicity, I'm going to start with P not equal to 0. Not to address Andrea's question, P is non-zero, but P could still be 0 mod 2N. So I'm including this case. So I'm going to pull out of a hat a new TQFT, which is the original one T. I tensor it with U1 level minus NP, and I gauge a Zn, diagonal Zn one-form symmetry. This is the other notation. This is the anion that I use in the gauging. A is from the first factor and charge P from the second factor. Comment number one, this is a valid gauging because the anion A has anomaly P mod 2N here, and the anion P here is the opposite anomaly here, and therefore we can perform this gauging. And this theory T prime depends on P and not only on P mod 2N. So at the level of the TQFT, only P mod 2N is important, but now this theory T prime that I pulled out of a hat, it depends on the integer P. Now I'm going to play another game and add another U1 gauge field to the story. This whole thing looks totally unmotivated at this stage. I understand that it looks totally unmotivated, but I think this is the simplest way to present it. I will later present more intuitive interpretations of it, and it will motivate the construction. So now I'm adding another U1 labeled by C, gauge field C, and write this Lagrangian. And this Lagrangian has a BDB term with a coefficient NP, and another term BC with a coefficient N. And we can redefine C by doing that shifting P, but let's not do that. So to relate to the previous discussion,
Wait, Nadi.
the U1 here,
U1 sub C, U1 sub C is not U1 level C. It's U1 with gauge fields.
it's not, that's completely right.
Yeah.
This is terrible notation. I could not put more scripts and subscripts. The U1 C is the U1 of the gauge field C, not to be confused with level C. The Lagrangian that I'm interested in is this one. And I know that it can be simplified, but I deliberately do not simplify it. So just to relate to what we said before, the U1 here in the numerator is this factor. And the gauge field C that I added is here. So doing that, I can put this whole theory here in the numerator, replacing U1 level minus NP with this Lagrangian, with this TQFT. And then the quotient that I will take is T times this new theory, modded out by diagonal Zn. And this diagonal Zn has A from the first factor, P times multiplying B, and minus 1 multiplying C. And the interesting thing is that this whole mess is isomorphic to the original T. So the anion in the denominator, that's what I said earlier, is this anion in the numerator. So in the numerator, we have the original TQFT T, and then the simple theory that depends on B and C. And out of it, I pick this particular anion, which is again order n. It has the appropriate anomaly such that the quotient is meaningful. And so this is a meaningful quotient. And the interesting thing is that this is a complicated way of expressing the original theory T. So roughly we can say that this C that we added removes B and removes the quotient so that we are left only with this T. I will soon, if you don't accept this quick statement, you're completely justified because this is indeed too quick, but I will soon do that in several different ways and you will see this is right. So what have we done so far? We started with the TQFT T, we mapped it to T prime, and then we added another field and wrote a very complicated presentation of the original T. Now, there are various other interpretations of this map from T to T prime. It appeared in this paper from 22. So this is the map that we have. We started with T and we found T prime. So way number one, we started with T, and we want to couple it to a U1. How do we couple it to a U1? We use the one-form symmetry of T, which is generated by A, and enrich T by another U1, and here B is not the level, but it's which gauge field carries that U1. So my convention is that uppercase is always a classical field and lowercase is a dynamical field. So I start with T, and I enrich it with a global U1 symmetry with the subscript B. And that means that the anion A of T is the Ison of this U1B. And then I'm adding a counter term. This is a classical field, so I can add a counter term with an arbitrary integer, n over 2 pi BDB. I have 2 pi here because I'm in the bosonic theory. And then I'm making B dynamical. And what it means in practice is that I'm switching from uppercase to lowercase. And then we see that changing this counter term here, changing n by an integer, has the effect of shifting p while preserving p mod 2n. So if we shift the integer n by 1, this is the same as shifting the integer p by 2n.
Are there two different n's here? Now I'm getting confused. Is big N the same as little n?
No, they're not. Little n is the order of the original anion A.
Okay.
And big N is an arbitrary integer that I can add an arbitrary SPT.
Oh, I see. That's shifting p. Yeah, got it. Okay.
And that the freedom in adding this SPT translates into shifting p while preserving p mod 2n. So this is another presentation, another interpretation of the map from T to T prime. So first I presented it as this quotient. I tensor something and I took the quotient. And presentation number 2 is go through these steps. Take the original theory, couple to a U1 gauge field, add a counter term, make the gauge field dynamical. That also gives us T prime. And the third presentation of this map is this is exactly the same as the abelian hierarchy construction of Haldane and Halprin. We will do it in more detail in the paper, but this map from T to T prime is exactly the same as this abelian hierarchy construction. We had T, we started with, and an anion A we started with. And now we take all these A's, and we consider many of them, and we put them in a fractional quantum Hall state associated with nu equals 1 over n, where n is this particular n. And the resulting theory, if you follow the abelian hierarchy construction, will give you exactly this construction. So we presented 3 different presentations of this theory, which are still pulled out of a hat. There are 3 different maps from T to T prime. So far, there's no field theory between them or anything. But before I go to more details, I would like to give some intuition about what's going on here. So we started with T.
Can I
Yes.
ask? So suppose that P and N are coprime, just for simplicity. Then
Yes.
if I want to essentially cancel the anomaly of the line that I'm discussing, there is simpler choice of the theory
That's correct.
to start with. That is the minimal TQFT.
I think I'm
Why are you
familiar
stuck in
with that.
non-minimal? Yes, but why are you stuck in this non-minimal theory?
Okay, I can tell you what happens if I do that. I can also, yeah, so why, so far, as I said, I'm putting it out of a hat. I could put here any other theory which has a Zn one-form symmetry and the appropriate anomaly. What you said is that in simple cases, there are simpler options. And that is correct. That's completely correct. But it turns out that this choice is extremely interesting. The other one is a little bit less interesting.
Okay.
But you could ask another question. If n and p are co-prime, this theory T also factorizes. And then there's a simpler formula for T prime. This whole business with tensoring and quotienting and all that basically replace the minimal with n and p with a minimal theory with p and minus n. So this map simplifies in this particular case that you mentioned.
Okay. Okay. Thanks.
Did I answer your, well, I didn't answer your question. You asked me, why did I do that? I do that because this one gives an
Yes.
interesting answer. But yes, there are other things I could do. There are simpler ones and more complicated ones. And the other ones are, we address all these things in our paper. So I want to give some intuition behind that. So we started with T, and we enriched it by U1, and made the U1 gauge field dynamical to find this T prime. This is what we said in the previous slide. And then we gauged the dual symmetry, the dual U1C symmetry to find back T. So that's what we said here. Now, this is very similar to the algorithm that performs the gauging. So here we limited ourselves to non-zero P, but the algorithm that does the gauging focused on P equals 0. So what was the algorithm there? We started from T, and we gauged the one-form symmetry, and then we gauged the dual zero-form symmetry to find back T. What we do here is very similar. We started from T with any P. Instead of gauging the one-form symmetry, we gauge the zero-form symmetry that uses the one-form symmetry for the enrichment. So we gauge that rather than the one-form symmetry. And then we could gauge back the zero-form symmetry. So the advantage is that in the procedure I'm doing here, when we gauge a zero-form symmetry, it's anomaly-free, and I can do that for any P. I should also mention that this map between field theories is very similar to the SL2Z action on field theories that Witten describes in 2003. And these operations of adding a counter term, gauging the dual symmetry, etc., are precisely the operations that you use there. So after this long introduction, I can finally describe my trend theory. So this is all the data we had before. We had T and we had T prime. And we could go back from T to T prime by performing this transformation. So we are going to write the Lagrangian for T, but using this picture. So this will give us a way of writing a Lagrangian for T. And now we singled out C, so we couple it to a scalar field, and this is our field theory. So the intuition is that
Nani, are you somehow using the subgroup of Witten's SL2Z? I mean, Zn is not a subgroup. So
Zn.
I'm not understanding the relation to Witten's SL2Z. I mean, I recognize that he used some of
Witten's SL2Z is generated by two operations on the field theory. One of them, you couple it to a background U1 gauge field, and you change the counter term. This was my integer n.
Yes.
The other operation was make the gauge group dynamical, make the gauge group, make the gauge field dynamical, and find a new theory. Yeah. This was the operation S. So this is very similar to what we do here.
Indeed. So I'm trying to understand are you looking at a subgroup of the SL2Z or?
I just did a particular transformation.
You're just looking at some transformation in SL2Z.
That's correct. The map from T to T prime is the particular SL2Z transformation, and the choice of P tells us which transformation in SL2Z. I'm just connecting it to, so far, this talk said nothing. All I said was that I proposed a problem, and then I said there's a map from T to T prime, which I presented from many different perspectives. So I have not yet answered the real question I was trying to address, which is the transition theory. Did I answer your question, Greg?
Yes. In principle, you could just tell me the SL2Z element and
Right.
Wait,
But
wait,
okay.
that's right.
wait, sorry.
Okay.
I thought Greg's question is that in Witten's story, there's no n, and he was wondering where did the n
Little n
go?
or big N?
Little n. And
That's
I
correct.
think
Well,
that,
there was little n. Little n was buried in the original theory.
right. I think the
And
answer to
wait,
Greg's question.
let me finish. In Witten's story, there was a theory, and we gauged, and it had a global U1 symmetry.
That's right.
This translates here to the TQFT, and a particular way of enriching it with U1.
That's right. That's right.
That's analogous to Witten's step one. There is a theory with a U1.
Yeah. Yeah. I think what Greg was missing is that the ZN one-form symmetry is enriched to U1 symmetry at the intermediate step on the previous slide.
Okay, I've known Greg for many years, and I learned never say what you think Greg missed.
All right.
I've learned that the hard way. So what's the story here? The whole complicated thing that we have done so far was to take the starting point LT and write it in such a way that we focus on one anion A, such that we can couple it to a scalar field phi. So the scalar field phi that we now threw in couples directly to C. So the field phi creates the anion A as this Wilson line. So this is the main point. The main point is that we, after all these gymnastics with T and T prime and little n and uppercase and lowercase and Witten's SL2Z and mod 2n or not mod 2n, that's what we ended up with. We rewrote the original TQFT in such a way that we single out one anion out of it, a billion anion, and we describe it as this simple Wilson line. And all the rest kind of makes it more complete. So now, once we've done that, I've presented the construction for non-zero p. The construction as it stands exists for all p's, including p equals 0. So now all we need to do is turn the crank. We have a well-defined field theory. This is it. And we could analyze it. So we have painfully done it. And we found a very detailed description of this theory for any T of A. It has very interesting and subtle global symmetries. This is my rule. When you're presented with a field theory, the first thing, find the global symmetry. So the coupling to phi, first of all, breaks explicitly some of the one-form symmetry of T. This is standard. Whenever we have charge matter fields, the one-form symmetry of the gauge theory is explicitly broken. And this is an example of how it can be broken. We'll soon see why this is significant.
Sorry, Nati,
Second,
could I ask a question? In the action in the Lagrange you wrote on the last slide, you didn't add this phi to the n. I think at some point you were talking about adding a phi to the n term. I don't know what
that was when the gauge group was the n.
Okay.
Originally, I said in the original presentation, there was in this theory for p equals 0, I had to add phi to the n, and because the gauge group that I gauged was Zn. Now I'm presenting something else. I'll soon explain the relation between them. Here, the gauge group is U1, and I'm not allowed, I cannot add phi to the n, it's not gauge invariant.
You could add
So
more.
I'm just going to study this theory, and we'll soon see the analog of adding the phi to the n.
Okay, thanks.
So what did we do? We analyzed the global symmetry. Since we have charge matter, the one-form symmetry is a little bit smaller. That's actually soon be interesting. The theory also has a global U1 symmetry. And naively, we just rotate phi by a phase. We didn't have phi before. Now we have something very similar. And the only difference, we can rotate phi by a phase. But you could say, wait a minute, rotating phi by a phase is a gauge symmetry because it was coupled to C. So that cannot be quite right. So this has to be corrected. And once it is corrected, I'm not going to give the details here. There is still a global U1 symmetry with very interesting subtleties. I'll mention some of them later. And the theory has a particular local operator, O, that carries the minimal charge under that U1. It is constructed out of various monopole operators of the various gauge fields and phi, etc. I'm not going to describe it in detail here, but I'll add parenthetically that this O will be the counterpart of Sakura's question about the phi to the n, as we will soon see. The next comment about this transition theory is that if we are only interested in the local features, because it's non-topological, so let's be careless about the global features. So all the gauge groups are R, we can neglect all topological excitations, then the local dynamics depends only on one rational number. It's a U1 gauge, it's a complex scalar field coupled to C1 with a Chern-Simons term that depends only on P over N. So locally, the dynamics at the transition is very, very simple, is independent of most of the details we've been discussing. And we can also perform particle-vortex duality transformation on that field theory. And that gives us the inverse transition, instead of transition from T to T prime to a transition from T prime to T. But let me describe it in more detail. What are the phases of the theory? If P is non-zero, there are two phases. When mu square is positive, we can forget about the scalar field and we have the phase with T. If mu square is negative, it Hickses C, and we have the same field theory, the same Lagrangian that we had before, but we can just set T to 0 and we find T prime. So this is satisfactory. We presented the Lagrangian, we pulled this construction with T and T prime out of a hat, but we now presented the Lagrangian that given T and A, it gives us a phase transition that implements the abelian hierarchy construction. When P equals 0, the situation is different. When mu square is positive, phi is still massive, and we have a gap phase with T. That's obvious. This is our starting point. But when mu square is negative, the theory as I wrote it is actually gapless. I mentioned this special operator that has the minimal charge under the U1 zero form symmetry. It has a non-zero expectation value and leads to the spontaneous breaking of this symmetry. So for one thing, this theory as it stands for non-zero P, it gives us the transition theory for the abelian hierarchy construction. But for P equals 0, it does not do the gauging. That's not the same as the gauging because instead it gives us a gapless phase. However, we can modify the theory, as Sakura already alluded to. We said that when mu square is negative, it's gapless, and the expectation of O leads to spontaneous symmetry breaking. But we can add to the Lagrangian the operator O that explicitly breaks the symmetry. It gaps the system and leads to the gauging. So this transition theory implements the gauging of the one-form symmetry, and in this case, indeed, the symmetry is anomalous. Relating back to Andrea's question, if I take the same Lagrangian and P is non-zero, but it's 0 mod 2n, in that case, this field theory does not implement the gauging. Instead, it gives us this other T prime that I mentioned earlier. Let's compare it with the gauging. When performed the gauging, and I stressed it earlier in the talk, there was explicit breaking of the one-form symmetry of T due to the gauging. So in the gauging procedure, a subgroup of the one-form symmetry, the one that the lines that do not commute with, that break non-trivially with the anion A, these lines are gone, and that can be interpreted as an ABJ anomaly. In this field theory of ours, this explicit symmetry breaking occurs through the coupling of phi. So the fact that phi couples to the TQFT, I mentioned earlier, this reduces the one-form symmetry. So the ABJ anomaly is seen here as a classical effect. Also, surprisingly, when we perform gauging, we often have a dual symmetry. I mentioned it earlier, the one that permutes, the lines are split in the gauging procedure. It permutes lines. This dual symmetry is an exact symmetry of the full transition theory. It's not an emergent theory in the other phase, but it is an exact zero-form symmetry of the full transition theory. So let me make some more comments. The transition theory implements the gauging for P equals 0. And this theory is the same as the construction of these people. Relating to Sakura's question, I had to turn on the operator O, which is a complicated operator. It's made out of, constructed out of monopole operators and so forth. And this operator plays the role of the phi to the n that had to be added to this theory. And locally, but not globally, the phase transition that we have here indeed looks like a condensation transition if we neglect the Zn gauge field. Because if we neglect the Zn gauge field, we simply have a transition where a system with a global Zn symmetry, the Zn is spontaneously broken. So that indeed looks like condensation. So that is a satisfactory story, but if we're interested in the fractional quantum Hall system, we would like to couple this whole setup to a global U1 symmetry. In that case, it's electromagnetism. So we would like to couple it to a U1A. The subscript A here is not a level. This is A, where A is the vector potential of the U1 gauge field of electromagnetism. So we started short distances with some lattice model or some gas of electrons, etc. And at long distances, we find T. And we ask ourselves, how does this U1 global symmetry act at long distances on T? And the answer was given by these people in 2004. It acts via enrichment. No global symmetry. The U1 global symmetry cannot possibly act faithfully on the TQFT. At best, we can have a discrete symmetry that produces lines. But as a U1 symmetry, it cannot act faithfully on the TQFT. Instead, it can act via enrichment, where the gauge field, you use the background gauge field A to construct the background gauge field for the one-form symmetry. So this is the process of enrichment that was explained beautifully in this paper. And then we ask ourselves, is this process of enrichment compatible with the transition theory that we described? So at very short distances, we have some lattice model or some UV theory of electrons. At very long distances, we have T or T prime, depending on which phase. But the hero of this story is a theory, a non-topological theory that acts at intermediate energies that captures the transition between the two phases. So I should first emphasize that this U1A that started its life at short distances is unrelated to the faithfully acting U1 symmetry that we talked about earlier. The latter acts on the local operator O in the transition theory. So we have kind of lots of characters in this story. In the transition theory, we had a global U1 symmetry, and it acts on the simplest operator it acts on is this O, which carries the minimal charge under this U1. And now we bring another U1 from the UV, and we ask, what's the interplay between these U1 symmetries? So the most interesting case is P equals 0. This is the one that leads to gauging. So let's recall what we had here. So before added P-O to the Lagrangian, O got an expectation value after the transition. So we started with T, and after the transition, O got an expectation value, and it spontaneously breaks this symmetry, and we ended up with a gapless phase. And if we add O to the Lagrangian, that explicitly breaks the symmetry and gaps the system, and leads to the gauging transition, to the transition that implements the gauging. So now let's take this setup and enrich this system with U1A. And now we have a split in the road, depending on whether the anion A, which is the one that triggers the transition, does or does not have fractional charge under this enrichment symmetry U1A.
Sorry, can I ask something? In principle, O could be irrelevant.
That's correct. That's perfectly correct.
In that case, in the infrared, you recover the U1 symmetry.
On the phase T, I recover okay, let's start in the positive mu square phase. O is irrelevant. It's a very high dimension operator. And I recover the symmetry that the U1's the zero form symmetry, but the zero form symmetry of the TQFT does not act faithfully on the TQFT. The TQFT does not have any local operators, so no zero form symmetry can act faithfully on it. Only discrete symmetries can act faithfully on it.
Okay, but you started in a situation in which you had a gapless theory because O was taking an
That's in the
expectation.
other phase. So let's start in the
okay. Sorry, yes. In
the original phase, O is irrelevant, but all these symmetries, the U1 0 and the U1 sub A, all these symmetries do not act in the infrared, do not act faithfully in the infrared. Okay, so it doesn't matter much. As we go to the other phase, when P equals 0, O is not only relevant, it actually has an expectation value. It has an expectation value and making the theory gapless. So now it's very, very relevant because it even has an expectation value. And I claim, I have not proved it here, but if the anion A has fractional charge under this symmetry, the operator O necessarily carries charge under this U1 symmetry. Now we have the standard picture. If we add it to the Lagrangian in order to find the gap phase that implements the gauging, that symmetry is explicitly broken because this O carries charge under this symmetry. If, however, we do not add it to the Lagrangian, we end up with a gapless phase, and then this electromagnetism is spontaneously broken. We have a superconductor on the other side of the transition. So this is if we take things at face value. If you tell this story to a TQFT person, that person will tell you, wait a minute, there is a third option. When we gauge a symmetry, a one-form symmetry, and the anion A has fractional charge under that enrichment, in that case, what we should do is extend this U1 symmetry of A. So we can extend the symmetry, and this is standard in TQFT. And what that means in practice is we just change the charge normalization. We change the charge normalization, the charge of A will no longer be fractional. And doing that, the charge of A, we can make the charge of, this is a typo, to make this should be A, little a, the charge of A should be an integer, and then we can adjust the coupling to phi such that O is neutral. So this is a complicated way of saying that in the TQFT, if little a carries fractional charge under the enrichment, then what we should do when we perform the gauging is extend that symmetry. So this is a procedure now that we can do in the full transition theory. But as we do that, we have to change the U1 normalization of the charges in the UV. So the upshot of all that, that if we start in the UV with P equals 0, with some enrichment, with some U1A, and anion A has fractional charge under it, then either the U1, the original UV symmetry should be explicitly broken. We definitely don't want that. Or we end up with a superconductor. We might or might not want that, but that's what the system does. In any event, that's not the gauging transition. Or we could modify the normalization of the U1 charge in the UV. So to summarize, if A has fractional U1 charge, the transition field theory for the gauging is incompatible with enrichment. And this really drives the message that gauging is not the same as condensation, because once we add enrichment, the two are incompatible with each other. I'm going to flash one quickly an example of it with the non-abelian theory so that to connect to things that some people here might be familiar with. Imagine we start with SU2 level K. Then the anion A that generates the one-form symmetry is the one with spin K over 2. It generates a one-form symmetry, and this is the value of the anomaly. And if P is non-zero, it maps T to T prime. This is T prime. So we have another one parameter for given SU, we're starting with SU2 level K. In this anion, we have a one parameter family of answers labeled by P. And here is just one example. If P equals K, this is the power fermion theory. So in this example, we start with T and write a field theory. It's a Higgs transition that maps the SU2 level K to the power fermion theory. And if P equals 0, and therefore K equals 0 mod 4, we have a transition to a gapless phase. If we add this O equals phi square, we add it to the Lagrangian, it implements the gauging, the standard gauging of SU2 level K to SO3 level K. So my time is over, so let me summarize with conclusions. First, I'll give a broad view of the conclusions and then a more detailed view. Anion condensation is a misleading name for gauging a one-form symmetry or for a hierarchy construction. Nothing condenses here. It condenses only in the sense that there are many such particles. This is the same as vapor turning into liquid, but it's not, this is not a meaningful characterization of the phase, as it is not a meaningful characterization when vapor becomes a liquid. Gauging a one-form symmetry is the same as proliferation of anion lines. This is just a statement that when we perform the gauging, we have to sum over insertions of symmetry defects. And the proliferation can be achieved by a phase transition described by a field theory. And we describe this field theory, the story breaks to two cases, but the formulas are uniform in P. For P equals 0, it leads to a transition to the TQFT. And when P is not equal to 0, this is the abelian hierarchy construction. And let me say it in more detail. We presented a unified treatment of many phase transitions. Out of a general TQFT, we started with a general TQFT, perhaps non-abelian. And they're all associated with the proliferation of the anion A that generates a one-form symmetry with a prescribed anomaly. And the transition field theory depends on T and A and on an integer P. And I said the surprise number one is that we can find such a field theory. Surprise number two is that there's an infinite number of them. And surprise number three, that all this infinity is summarized by one integer. I did not describe in detail here the subtle zero-form and one-form symmetries, but there's an interesting interplay between these symmetries of the transition theory and what happens in the TQFT. When P was not zero, we have a transition from this T to this T prime, and that's the abelian hierarchy construction. And when P is zero, we have a transition to a gapless phase. And finally, if we have P equals 0 with an appropriate deformation, the transition is from T to the gauge theory. T prime is T mod Zn, and that's like gauging the one-form symmetry. And finally, in some cases, this is incompatible with the enrichment of T. So these are the conclusions. I went a little bit over time. I'm sorry about that. And thank you for listening.
Okay, thanks very much for this nice talk. Are there any more questions?
So I have a question.
Okay, Sal? Sorry, Sal put his hand up first, I think.
Okay. Thanks, Nati. So my question is, how special is T being a TQFT? It seems like a lot of this talk could be generalized to the case where T is a QFT and it has some one-form symmetry.
That's correct. That's correct. But I wanted here a separation between the two phases. I wanted to start from a given phase and then find the transition. Now, if T is not a TQFT, there is a gap, and then there are some other modes in the theory, and I cannot separate them from the other modes that I'm throwing in. So you're right that we can take any field theory and use an apparatus similar to this one and embed it in a bigger theory and find the transition. But I'm not going to have then this clear separation of scales. So the way we worked here is we started with a TQFT that was unambiguous. And then we wanted to write a field theory where the anion is dynamical. And this is meaningful because the anion is separated from the TQFT because it is at higher energy. So we start at low energies, we have the TQFT, that's at zero energy. And then one anion comes down, or maybe multiple anions come down. And now we would like to write something that describes this anion and the TQFT. If, however, you start from a non-TQFT at the starting point, there will be two stories. One, the anion that comes down is heavier than the field theory you started with. And the other is when it crosses to low energies and it is the lightest mode. So the story has many more options.
I see. So maybe I think you kind of did. So if I try to do this with some linear sigma model, you say maybe there'll be some intermediate phase that happens.
Right. There will be many more options. There will be many more options. So as I said here, the surprise number one is that we can actually do that. We have a very simple field theory that implements all these transitions. Surprise number two is that there's an infinite number of them. And surprise number three is that the infinity is not that big. And there's a canonical construction.
Okay. All right. Thank you.
Hey, Greg?
Yeah. So I'm wondering about the about experiment. I mean, it's sort of a two-part question. So is there a way of giving experimental realization of your theory with phi, and on the flip side, when we see talks about the fractional quantum Hall effect, they plot these the resistivity as functions of of the magnetic field, and then we see the dips where they're the different fractional Hall
Yeah.
states. So isn't that in nature a transition between these different fractional Hall states?
It is, but I think it's typically a first order transition, if at all. Whereas here, I try to find a second order transition between them. And whether this transition actually exists in nature, I'm a theorist. I don't know anything about experiments. I love experiments, but I know very little about what is being done there.
Okay,
I would be delighted if this particular field theory can be realized experimentally. But more conceptually, I find it satisfying that these intuitive pictures that the condensed matter people had, take the anyons, create a fractional quantum Hall of the anyons, and find another state and all that I never understood what it means. Now I say, oh, all they do is find a particular presentation of the TQFT and throw in a scalar field that couples to it in a particular way and give it a value. So these are steps that I understand. Now, whether it agrees with experiment is really beyond me.
Well, I was just wondering if there would be, I mean, since we see transitions in nature as we dial a parameter, you might ask if there's a field theory, but you say it's first order. So if yours,
no, I didn't say I did not say it's first order. I said it
I
might
thought you
be.
just said it was first order. I didn't actually know that. Well, let's take your theory. So what happens if we make mu squared a function of x? So we have a domain wall. So we have a
Excellent
Janus.
question. Excellent question.
So do we get a conformal 2D conformal field theory on the
I
domain
assume
wall?
that the answer is yes. It would be the interface between T and T prime.
Yeah.
So this
So
would
do you know
really
what
be the
can you describe what conformal field theory is? It's probably its
I think it
rational.
would be straightforward. In fact, I think I actually worked it out with Mong because Brandon asked me exactly this question a few months ago.
Okay.
And we worked it out. So you have in mind mu square varying in space from being large and positive to
So
large
it
and
varies
negative.
along some axis. It varies
Yeah,
linear.
and then
space.
right, and then there should be a 1 + 1 dimensional field theory on the interface.
Correct.
And it should be the one that interpolates between T on one side and T prime on the other side.
Yeah, I'm just wondering, I mean,
this would give you a particular construction because it could be
we have different CFTs, which are holographic descriptions of the two different topological theories. So which one is?
Right. So in general, there could be many different field theories that interpolate between T and T prime, and this particular Lagrangian will give you a preferred one.
No. On the domain wall, we should have I'm thinking that on the domain wall, I'd want to put the 2D.
Greg, you'd like to be precise with the language. This is an interface. This is not a domain wall.
Okay, thank you. Yeah, on the interface, I'd want to put the 2D conformal field theory, which is holographically dual to the Chern-Simons. But which one?
You could do that, but I'm saying that this field theory, that once you are within the realm of this field theory, you don't have the option. You vary mu square, and the field theory does what it wants to do. And what I believe happens is some of the modes in phi will be massless there, and they will interact with these various gauge fields, and you can work out very explicitly what the light modes on the interface are. And it will be something that has the right anomaly to be the theory on the interface between T and T prime. And I really emphasize it. Normally, when you study such interfaces, you have the option of adding something else there. And the reason is that the data is the TQFT that you started with. You say, if T here and T prime here, what can I put in between so that all the anomalies match? In this framework, I've already given you
a particular theory.
I have a particular theory, so you can calculate, and what you calculate will have to satisfy the anomalies unless we messed up in this analysis.
Sure. Okay.
Mong, do you want to add something to this?
Yeah, I'll just add quickly for Greg's question about the interface theory that you can easily see that the theory has to be a C equals 1, the central charge C equals 1 theory, just from the expression of T prime. Yeah, so I just want to add that.
Oh, I see.
Yeah, thank you
for any K matrix. For any K matrix, that's surprising.
No, it's not surprising because the difference it's for any T. Thank you, Mong, for reminding me. That's true for any T. Because the difference between T and T prime is
the extra U1.
The U1, yes.
We tensor another U1 and we gauge something. So the difference between them is only within the U1.
Yep, got it.
And thank you, Mong.
So you mentioned that you will not discuss non-invertible symmetries, but you expect a similarly sort of elegant picture to exist there, or
I
will
would
become much
love to
more
see a
messy?
similar, yeah, I would love to see that. I think this is, yeah, the quick answer is yes. I would bet there is a beautiful story for non-invertible symmetries, such that all the algebraic things that are being done at the level of the TQFT can be done at the level of this non-topological field theory.
Mm.
But I haven't done that. It's not easy. I tried a little bit. I did not get very far. It's not easy, but there are examples. Clay Cordova and his collaborators wrote recently some relevant papers with such non-invertible symmetries, gauging non-invertible symmetries via Higgs transition.
Mhm.
And maybe some clue can be found from there.
Exactly. Yeah. Okay. Are there any other questions? If not, then I'll stop